While last week everyone and their mom was busy slam dunking on the Blizzard guy, I was watching people run Doom on a pregnancy test, which turned out to be fake. And let me tell you, if there's one thing I do have experience with, it's fake pregnancy tests. Anyways, somehow I ended up in the YouTube rabbit hole of running Doom on calculators. I saw people just drag and drop some files, press a button, and boom, now you're shooting demons in the face with a shotgun on a calculator. And as an embedded software engineer, that made me wonder, how does this actually work? I mean, what even is this device? How does the hardware look like? Is it running bare metal? Does the calculator have an operating system? Some kind of layered architecture? What language do you even write calculator software in? Since I had more experience in pregnancy tests than in calculators, you can imagine I had a lot of questions. And that's where my journey began. At first, I wanted to get the original classic TI-83 Plus. So, like everyone else, I went straight to Amazon to help my boy Jeff get his next yacht. But turns out the TI-83 cost like $200 for a calculator from the 90s. Alright, fine. So my second option was to get a used one. And that's when I found out that TI-83 uses a weird ancient data link cable that's basically impossible to find. I kid you not, I spent a whole week trying to order one, and when I finally found someone selling it, they canceled the order the next day saying it's out of stock. Cool. So I started looking for something with a similar hardware but with a USB port that's not from the Stone Age. That's when I found out that the TI-84 Plus is pretty much the same as the 83, just with better specs. It has the same Z80 processor, just clocked faster, more RAM, more flash storage, and most importantly, a normal USB mini B port. Now, keep in mind we're running Doom as an application. We're not writing low-level code. So having the same instruction set means things should work. Should. Okay, so since my dad doesn't work at Blizzard, I went to eBay and bought a used TI-84 Plus for like $7. I loaded everything and surprisingly, it just worked. I was surprised because when you're dealing with embedded systems, everything, and I mean everything, can go wrong. Don't believe me? In safety-critical embedded systems, you even have to protect against cosmic radiation. Because yes, space can flip and will flip a bit in your airplane control system. Welcome to embedded development. Okay, so I finally got the calculator. But what even is this device? Okay, now looking from a very top perspective, we know that the device has some inputs such as the keyboard or the USB port, and as the output we have the LCD display. Furthermore, we have this 2.5mm port which looks like it's used for audio, but it doesn't have anything to do with sound, it's just a serial input and output. I mean, the calculator doesn't process any sound. But this calculator is still a black box to me. We don't really know what kind of software stack it's running. I mean, with microcontrollers, you got a few options. You can go full bare metal, no operating system, no layers. Then you can just raw dog directly control the hardware. Or you can write some monolithic firmware that does stuff like reading key presses and doing calculator stuff. That's it. But in this case, you can load custom application into the device and run them. Now, the most interesting thing that I observed in this device was that you can just switch back to normal calculator mode like nothing happened. And this seems trivial, but anyone working in embedded knows that you usually don't create a built-in restart functionality. So if you want to restart the application, you have to restart the whole device. And that's why turning it off and on works in many cases. So that made me think, okay, maybe the architecture looks something like this. At the bottom, of course, we got the hardware. Then we have a firmware layer, maybe something like a tiny operating system. And on top of that, we have the application layer. The application layer then uses whatever functions the firmware provides. And the firmware takes care of memory management when starting and exiting an application. Sounds reasonable. That was my assumption how this system works. But I wasn't satisfied with this surface level understanding. So I started digging. A lot of people watching this, and myself included, are not hardware engineers. But in my opinion, you should be able to take a look at the board and identify at least the ASIC and the flash ROM. So if you open the calculator, here's what you'll see on a very top level. We have the ASIC at the center, so the TI-84 Plus integrated the CPU, the RAM, and the USB logic into the ASIC. We have the flash chip, then we have the LCD cable, and at the top we have the USB mini port, the serial I/O link port. Now, the TI-84 Plus runs on a Zilog Z80 processor, clocked at 15 MHz with a 6 MHz compatibility mode. This is a classic 8-bit CPU first released in the 70s, and it was commonly used in early home computers. People like to call it a simple instruction set because it has only about 150 instructions and a clean syntax. You don't need dozens of addressing modes or complex register sets. Now, if anyone is interested in this, I will link the Z80 instruction set manual. You can go in and dig deeper if you want. I'm not saying you should go and now learn the full Z80 instruction set, but I think it's pretty interesting to see how this type of document is structured. And of course, learning how to read and understand data sheets properly is something I would recommend anyone. Then we have the flash ROM memory, which on the T84 Plus is 1 megabyte with about 480 kilobytes usable for the user. The flash is of course non-volatile in this case. Volatile meaning it keeps your programs even after you remove the batteries. Then the calculator technically includes 128 kilobytes of RAM, but only 24 kilobyte is accessible to user programs. Now, if you're wondering what's the reason for this, well, some space is reserved for the operating system, some is used to dynamically map memory banks in and out, and then yeah, you're just left with 24 kilobyte. Okay, since we already mentioned the flash memory and the RAM, let's talk about something very interesting: bank switching. I'm gonna go now low level for a second and talk about how the CPU in your calculator actually reads and writes memory. The Z80 has a 16-bit address bus. That means it can only see 64 kilobyte of memory at a time. That 64 kilobyte is like the CPU's personal window into memory. From the CPU's perspective, all memory lives in this address range. But the calculator actually has way more memory than that. We have 128 kilobyte of RAM and 1 megabyte of flash ROM. So how does the CPU access more than 64 kilobyte if that's all it can see? And that's where bank switching comes in. The 64 kilobyte address space is split into 4 regions. The CPU 64 kilobyte view is always structured the same way. So each region is 16 kilobyte, the first block is fixed, it always shows flash page 0 which contains core operating system code. The other 3 blocks are swappable, and you control what page is visible by writing values to special I/O ports, ports 6, 7 and 5. Now we're gonna walk through a read example. Let's say the CPU wants to read a byte from the address 0001. So in the first step it puts the address on the address bus, it raises the read signal, and then the data bus waits for a response. Now, since the address is in the 0 to 3 FFF range, and that range is always mapped to the flash page 0, the flash chip responds. It sees the address, checks the value stored there, let's say it's a AAA, and then it puts the AAA on the data bus. The CPU then reads that value and stores it in a register. Instruction complete. Now imagine the CPU wants to read from address C005. That falls into the C000 and FFFF range, which is used for RAM. But RAM is also paged. Each 16 kilobyte page of RAM lives at a different physical location in the full RAM space, like page 0, page 1, page 2, and so on. So, for example, the address C005 on the CPU side might actually refer to offset 5 inside RAM page 3, depending of course on which page it is currently mapped. So here's what happens. CPU puts the address on the address bus, it raises the read line, and the currently selected RAM page responds and puts a value, let's say BBB, on the data bus. And finally, the CPU grabs the value. Now, this is important. The CPU never sees the full 128 kilobyte of RAM address space. It only sees 16 kilobyte of RAM at a time. What's behind that range depends entirely on what page is selected. So CPU address C005 doesn't equal physical RAM address C005. The address always gets translated depending on the active memory page. Now, another important thing is all of this happens over shared buses. So the CPU, the RAM, and the flash all share the same address bus and same data bus. But only one device is allowed to respond at a time. And that's based on two things. First, which address range the CPU is accessing, and second, which page is currently mapped for that range. There is no external memory controller. The logic for handling all of this is built into the TI ASIC. It uses the CPU's I/O port rights and address lines to decide which chip, RAM, or flash should respond, and which physical page of memory should be mapped into which region. Only the correct chip is allowed to drive the data bus. The others stay quiet. And that's how the system avoids collision. Now that we know the CPU only has access to 64 kilobytes at once, let's see how bank switching works to show more memory. The CPU's address space is fixed, from 0 to FFFF, but the calculator's hardware can swap in different 16 kilobyte memory pages into specific regions of that space. Say you write the number 4 to port 6. That tells the calculator, please map flash page 4 into the 4000-7FFF range. Now, whenever the CPU accesses that address range, it's seeing page 4 of the flash. And this is how large programs like Doom are able to run. They aren't copied into RAM, instead they stay in the flash and the calculator just swaps in parts they need while they run. Now, another neat thing is execution in place. The Z80 can run code directly from flash. This is called execute in place, or XIP. Once a flash page is mapped into the CPU's address space, it can fetch and execute instructions from there just like it would from RAM. And that's a big deal because it means code lives in flash, which is read-only, and RAM stays free for dynamic allocation stuff like game state, input, frame buffers, and so on. But one thing to be careful about is, if your code is running from a flash page and you swap the page out while it's executing, the CPU will crash. And that's why shells like MirageOS manage the mapping carefully. They set up the memory pages before launching a program and clean everything up afterwards. Okay, enough about bank switching and memory, let's continue with the hardware. Now, before we continue, if you like the content, hit like and subscribe. Last time only 5.8% of my audience was subscribed to the channel, and now we are at 7.5, baby.
We are back, baby!
I also want to take the chance and say a big thank you to my Patreons and YouTube members. If you want to help me get better equipment, you can become a Patreon, the link is in the description. So we also have the monochrome LCD screen with 96 x 64 pixels. Each pixel is either on or off. No color, no grayscale, no alpha blending. There's also no frame buffer, so instead the CPU writes data directly to the LCD's memory. You send pixel data and the LCD updates immediately. This means drawing operations have to be tight and very efficient, especially for something like Doom that redraws constantly. And last but not least, we have the keypad, which has a matrix layout. Now, to understand how powerful this calculator really is, let's compare it to something familiar: the Game Boy. I know these devices are meant for totally different things, but comparing them side by side gives us a great sense of how just capable this boring calculator is. So let's start with the CPU. The 84 Plus is a Z80 processor, running at 15 MHz. The original Game Boy used a custom Sharp CPU, which is a hybrid between the Intel 8080 and the Z80, running at 4.19 MHz. So the calculator is based on a similar instruction set family and beats the Game Boy at the clock speed. Now you have to keep in mind clock speed isn't everything. The Game Boy CPU was tightly integrated with the rest of the hardware, which brings us to the RAM. The Game Boy had just 8 KB of main RAM plus 8 KB of video RAM, so 16 KB in total. The calculator has 128 KB of RAM. although only 24 kilobyte is directly accessible to user programs. Still, it has a lot more RAM than the Game Boy. Storage. The Game Boy used swappable cartridges with ROM sizes up to 1 megabyte. The calculator has 1 megabyte of internal flash storage, with about 480 kilobytes available for the user. So in terms of storage, they are kinda comparable. Graphics. Here's where things really differ. The Game Boy had a built-in 160 x 144 pixel display, with hardware support for tiles, sprites, and scrolling. It had a real PPU, a picture processing unit. The calculator, on the other hand, had a monochrome 96 x 64 pixel display and no graphics hardware. So every pixel you draw has to be handled manually in the software. No tiles, no sprites, no acceleration. And that's where proper system design shines. If you scope the use case properly and then design the system specifically for only that use case, you can handle it with minimal specs. Sound, the Game Boy had a sound chip built in, the calculator didn't have any sound, and for the controls, both devices had some kind of keypads. So, what does all of this mean? From a pure numbers perspective, the TI-84 Plus is way more powerful than the original Game Boy. Faster CPU, more RAM, more storage. But the Game Boy was engineered from the ground up to play games. It was specialized for that use case. It had hardware acceleration for the exact things games need. It was optimized, lean, and purpose built. The TI-84, well, it was designed to grab stuff and write 80085, not shoot demons. So while the calculator can run games with some clever tricks, it's actually doing way more work behind the scenes than the Game Boy. And that's what makes Doom on a calculator so impressive. Not because the hardware is powerful, but because it was never meant to do any of this. Okay, now let's take a look at the next layer of our architecture, the firmware. The TI-84 Plus runs on an operating system called TiOS. It's not Linux, it's not Windows, it's not DOS. It is a custom-made OS made just for these calculators, and it lives entirely in flash memory, taking up about 520 kilobyte. TiOS is the layer that sits between the hardware and everything you run, the applications, the TI basic scripts, or assembly programs. It handles the menus, the math interpreter, the graph system, input handling, and all the logic behind loading and executing code. When you turn on the calculator, it boots straight into the home screen. You can enter expressions, run programs, and navigate the menu. It also includes the TI Basic Interpreter, which most students use to write small math scripts. It is pretty limited and slow, but it works. Now, an important thing to mention is the TiOS handles memory management in the RAM, but it doesn't really manage execution of programs stored in flash. So when you run a small assembly program that lives entirely in the RAM, TiOS can launch it, give it control, and bring you back safely when it exits. That's completely fine. But when you're trying to run something bigger, like Doom, which lives in the flash and spans multiple memory pages, TiOS doesn't help much. It doesn't automatically map the right pages into memory, it doesn't prevent you from paging out your own code, and it doesn't clean up after crashes. And that's where shells like MirageOS come in. MirageOS fills this gap. It gives you a file browser, shows icons for your programs, handles paging flash into the right memory banks, launches your code safely, and brings you back to the menu when you're done. So TiOS gives you just enough structure to run code. But if you're running anything big, anything flash-based, or anything that spans multiple memory pages, you'll quickly run into its limits. And that's exactly why MirageOS exists. So MirageOS doesn't replace TiOS, it just runs on top of it. But it adds the missing pieces that make complex programs actually runnable. But before we dive into the details of MirageOS, let's take a look at B calls. Okay, now, as you know, in a normal operating system like Linux, Windows, or even DOS, your programs don't directly control the hardware. If you want to print something, read input, or draw to the screen, you make a system call. That's the operating system's job. It provides, so to speak, safe functions your program can use. Now, in the case of these calculators, if you're writing in C80 assembly and you want to talk to the operating system, maybe to clear the screen or print a text or read a key, you don't call a function directly. You use what's called a B call. B call stands for banked call, and it's the TIOS equivalent of a syscall. It's how your code asks the operating system to run one of its internal routines, without needing to know exactly where that routine lives in memory. Why do we need this? We need this because of how memory works on this calculator. The Z80 CPU can only see 64 kilobytes of memory at a time, remember? But the OS is bigger than that, and a lot of its functions are stored in swappable flash banks. So the code you want might not even be visible to the CPU at that moment. And that's why we have B calls. For example, it can look something like this. This first line is an actual Z80 instruction. It jumps to a fixed spot in the ROM where TIOS has set up a B call dispatcher. It's some kind of like a syscall handler. And the second line just places the function ID of the routine you want to run. In this case, this is the ID for the clear screen routine. So what happens? The CPU hits this, jumps to the dispatcher, the operating system reads the next 2 bytes, it looks that up in a big table of routines, it swaps in the right flashbang if needed, and then it jumps to the actual routine and runs it. When the routine finishes, it returns to your code like nothing happened. What's nice about this is you don't have to hard code memory addresses, you don't have to worry about bank switching yourself, and your code keeps working across multiple TIOS versions as long as the B call ID stays the same. So the banked calls are basically your bridge into the operating system. They give you access to screen drawing, keyboard input, LCD control, and so on. So yeah, B calls are the system calls of TIOS. And if you're writing anything in assembly on this calculator, B calls are essential. Okay, now let's finally talk about MirageOS. Now, if you watched videos where people run Doom, they always loaded alongside the Doom file also the MirageOS onto the calculator. But if the calculator already has a firmware, why do we need another layer? What even is MirageOS? If you want to run Doom on a TI-84 Plus, you don't just send the game file and hit run. You need something that knows how to launch it, where it lives, and how to clean up at the end. MirageOS is more than just a fancy menu. It's a shell that lives in Flash and runs on top of the TIOS. You launch it like any other app. From there, you get a clean interface, a list of programs, little icons, folders, basically a launcher for real games and utilities. But here's the magic. When you select a program, like Doom, MirageOS doesn't just run it. It handles everything behind the scenes. It finds the program, it sets up the memory, it maps in the code from Flash, jumps to the program's entry point, and when you quit, it resets the screen, clears RAM if needed, and drops you right back to the MirageOS menu. Without Mirage, running Doom is a mess. You'd have to unarchive it manually, type in ASM program Doom or whatever, hope the RAM setup is right, and pray it doesn't crash. So this little tool automates all of that, and it keeps it clean. One of its best features is that it can see and launch programs that are archived. Normally, TIOS can't run archived assembly code. You would have to unarchive it first, which then would also waste additional RAM. So MirageOS solves that. When it starts up, it scans the calculator's memory for compatible programs. These are programs that follow a specific structure. They have a MirageOS header, a noun signature, and sometimes even a 16x16 pixel icon. If a program checks out, Mirage adds it to the menu, even if it's sitting safely in the flash. You don't have to touch the memory menu. You don't have to unarchive anything. Now, here is where it gets more technical. When you launch a program, Mirage finds the program's Flash page and starts the execution directly from Flash, using the execute in place that I mentioned. This means the actual code for Doom, for example, stays in Flash. Mirage isn't copying it into the RAM. Instead, it just tells the calculator, here, look at this Flash page as if it's part of your own memory now. This means the actual code from Doom stays in the flash. Mirage doesn't copy it into the RAM. I mean, RAM is still used, but for other things like data, variables, and so on. Another important thing to mention when talking about MirageOS is it also standardizes the application format. So developers know their application will work consistently. So an application developed for MirageOS has to include a MirageOS header. Standardizing the development gives you a guarantee that your application, if developed according to the MirageOS rules, it will run on the device. But why is this approach good? Well, without MirageOS, you would have to manually handle the archived files, do memory management, and ensure that your application shuts down properly. So, MirageOS turns this fragile process into a, let's say, smooth experience. Okay, so we have talked about the hardware layer, the firmware, MirageOS, and now let's take a look at the Z80 Doom port. So first of all, this is not the full PC Doom engine running here. It's not id Software's Doom with a hardware abstraction layer wrapper. This is more like a minimal Doom version. And if you really think about it, it has more similarities to Wolfenstein 3D than Doom. The game you're playing is a heavily cut down Z80 assembly coded Raycaster game made specifically for TI calculators. It's a technical stunt, really, and it's brilliant. Just like today's sponsor of the video. Brilliant. You know how you keep saying, I really want to learn more about quantum mechanics? Yeah, no, you don't. But Brilliant makes it so painless you might actually do it this time. They teach logic, computer science, AI, and even quantum stuff. No lectures, no filler, just short, interactive lessons that make your brain wake up. I use it when I'm pretending to listen in meetings that should have been emails. It's like scrolling, but productive. And the best part, you don't need to be a genius. Brilliant starts simple and builds up gradually. So if your attention span has been absolutely fried by short form content, this is like rehab for your brain. Click on the exclusive link in the description or scan the QR code on the screen to try everything Brilliant has to offer for free for a full 30 days. You will also get 20% off an annual premium subscription. So yeah, rewire your dopamine loop and learn something useful. Now back to the video. Okay, so you can download the game and source code from this website. I'll drop the link in the description, of course. The whole folder is about 72 kilobytes in size. When you open it up, you'll see this .8xp file. That's the one you actually run on the calculator. But what we're really interested in is the source code. So ZDoom is written in Z80 assembly. You can recognize the source files by the .z80 extension. In total, there are 13 source files. I'm not sure if all of them go into the final build or if some are just for debugging or tooling. But either way, that's the full project. Now, because this is written in Z80 assembly, I'm not gonna walk through the code line by line or explain how the Raycaster works, and I got two reasons for that. First, Z80 is a pretty niche language. And second, if you actually wanted to learn how a Raycaster works, this is not the code you'd start with. There's just not enough value in spending hours trying to decipher low-level raycasting logic written in Z80. The cost-benefit ratio isn't there. Unless, of course, if it brings you joy. Like for example, I don't know, feeding birds. I get no real benefit from feeding birds, but it's kind of fun and that's enough for me. Anyway, looking at this from a high level, what really surprised me is how modular this code is. I expected it to be like one giant file with one giant main loop, but it's actually broken down really well. So you have separate modules or files for the AI, display, levels, menu, raycasting engine, sprites, lookup tables, saving the game, interrupt handling, and so on. And then of course you have the main Doom file, this doom.z80 file, which contains the main loop. If you open that one up, it starts by defining some variables, then it calls the init function, then we call the pre-main loop, and then comes the actual main loop. What I like most about this main loop is how readable it is. It basically says call the raycaster, draw the walls, draw enemies, draw weapons, draw the head-up display, and that's it. And what's funny, it's even rendering things in the same order as the original Doom. If you've seen my Doom code review video, this will feel really familiar. Now, another cool thing is the game actually has multiple levels. If you check the levels.z80 file, you'll see they use a Python script to compress the level data before it's compiled. I didn't have the time to figure out how this level format works, but they're compressing something. Now, for me, the biggest lesson, the biggest takeaway from this project is even if you're working on a small project like this calculator Doom project, you can still think about architecture and modularity. And in this case, my opinion, they did a really good job. So if you have the time and the calculator, of course, go grab the code, poke around, modify it, compile it, and maybe try to run it. Conclusion. So, what do we take away from all of this? You've just watched Doom run on a calculator, not because the calculator was powerful, but because it was flexible. Because it was designed in a way that allowed curious people to dig in, understand it, and make it do things it was never intended to do. And that's the magic of good system design. It's all about architecture. The TI-84 Plus is simple, sure, but it also has its layers. You got hardware that exposes ports directly, so no cryptographic lockdown. You got a firmware layer, TiOS, that's not open source but also not actively hostile. You've got a shell layer, MirageOS, which is built by the community. And on top of that, you got applications like Doom, for example. This kind of layer design, hardware, firmware, shell, application, lets you play around the device. It lets you build things. And it doesn't assume that the user is an idiot who will break the device. It assumes the opposite, that the user might want to do something different. And nowadays, this kind of trust, this kind of openness, it's rare. I mean, Texas Instruments could have easily locked this all down. This calculator wasn't built to be a game console, but the way it was designed made it possible. And that's the difference between a tool and a toy. A toy is fun once, and a tool is something you can turn into whatever you need. And this is the real lesson. In a time where everything is locked down, subscription-based or glued shut, here's a device from 2004 that still boots, still runs code, and can still be reimagined into something new. Maybe not everything needs to be thrown away. Maybe the best thing you can do sometimes is take something old and try to repurpose it. Or try to do something creative, like running Doom on a calculator. And once you understand how the pieces fit together, like CPU, RAM, flash, memory mapping, shells, you realize this. Sometimes you don't need more power, you just need the access. Repurposing old hardware isn't just a hobby, it's a statement. It says, this thing still has value, and I get to decide what it is for. And in that way, running Doom on a calculator is more than just a meme. It's a reminder that openness is freedom. Okay, so that's it for today. If you liked the video, hit like and subscribe, and see you in the next one. Tariq 10x.